So we're going to take some of the concepts we've been discussing about how we can understand how electrons surround the molecules. As described by quantum mechanics, we're going to take it to another level of theory. We talked about Lewis structures that helps us understand, understand the ideas at the level that, molecules want to feel octets. We went into valence bond theory, and that helped us understand hybridization a little more. We're going to take a more complete picture, a more complete theory of what's going on, looking at molecular orbital theory. We'll just be touching on that. You can get a lot deeper in this theory in other classes, but this gives you a more complete picture of what's actually happening in molecules. Yeah, so molecular orbital theory is what we're going to be talking about. When we talk about the orbitals as not merely being on the single atoms, but as being spread out throughout the molecule. Okay, so the learning objectives today, we want to explain how bonding and anti-bonding orbitals are created from atomic orbitals and calculate bond orders from molecular orbital diagrams. So we'll do this with some simple atoms, and then in another segment, we'll handle more complex atoms. Okay, so the difference between valence bond and molecular orbital theory. In valence bond theory, the hybrid orbitals are weighted linear sums of valence atomic orbitals of a particular atom. And the hybrid orbitals remain localized on that atom. We talk about a sp3 orbital on a single carbon atom, forming a sigma bond with a 1s orbital on a hydrogen. In molecular orbital theory, the molecular orbitals are still weighted linear sums of the valence atomic orbitals, but of all the atoms in the molecule. So the molecular orbitals can be delocalized over the entire molecule. You take atomic orbitals, you combine them, and you create orbitals that are spread throughout the molecule. So LCAO is the way this is described, a linear combination of atomic orbitals, but they're combined in a different way. So remember wave functions? This is where it becomes important. We talked a lot about wave functions being positive or negative, and the probability was what was important, because if you're looking at the probability, you looked at the wave function squared, and so you had nodes between where the wave function was positive and negative. But when we were just looking at probability of observing electrons around atoms, we didn't worry about the sign of the wave function. Aha! Now the sign of the wave function actually comes in. Rather than combining probability distributions, where we take the wave function squared, we literally combined wave functions. So how do we do that here? So let's say we have two hydrogens. They each have a 1s orbital with one electron each of them. So what we do is we form two new orbitals, but we form those two orbitals by adding the wave functions together and subtracting the wave function. So when we're dealing with two separate molecules, we say, okay, what we're gonna do is take this wave function, and then this is all positive, and this one is all negative. Remember, with an isolated atom, it doesn't matter whether they're positive or negative. It's sort of an arbitrary choice. But now when we form two orbitals, we form one orbital in which one wave function is treated as negative of the other, and the other where it's treated as the same as the other. So the additive combination creates, if you add up the wave functions, you get, with the same phase, you get constructive interference everywhere. You get an orbital spread over the entire atom that now is interacting with both nuclei. But now if you add the orbitals together with opposite phases, then it's going to be positive on one side, and then you'll have a node where the two of them cancel out to zero, and then you'll have a negative orbital on the other side. Now, as we remember, when you have more nodes, it's higher energy. So we have a lower energy orbital and a higher energy orbital. And so that's what happens when we talk about adding the wave functions together rather than the probabilities together. We get these two orbitals. So let's talk about this a little more. So the two atomic orbitals together make two molecular orbitals. We call the lower energy orbital the bonding orbital, and the higher energy orbital the anti-bonding orbital. And why do we call this bonding and anti-bonding? Well, when we combine the two orbitals together, one becomes lower in energy and the other becomes higher in energy by essentially the same amount. When we just have two equal atoms, it's actually, they go up and down by the same amount. So when we bring the atoms closer, the bonding orbital becomes available. And so it's lower in energy for the atoms to approach each other, because then rather than being in each electron being in separate orbitals on the separate atoms, they can both occupy the bonding orbital that is shared between the atoms. And the anti-bonding orbital, there's no electrons in it. There's only two electrons. So we fill up the orbitals, we fill up the bonding orbital, and we filled it up. All the electrons have a home, and that home is lower in energy than it would have been if they were on the two atoms alone before the orbitals combine. So we bring the hydrogens together, we form, instead of, now the electrons start noticing the other nucleus, they can start jumping back and forth, and two new orbitals are created, a bonding orbital and an anti-bonding orbital. So when we talk about the bond order of this interaction, so the antibonding bonding orbital is higher in orbital than the atomic orbitals. The bonding orbital is lower in energy than the orbitals that came together to combine it. Okay, so this is what we'd call a molecular orbital diagram. We've got the atomic orbitals over here that combined. They've each got an electron. And then we combine the two, and we have the bonding orbital, and this is called the sigma 1s. It's a sigma orbital because the same as sigma bonds. We're forming a bond out of this orbital. A sigma 1s because it's being formed from 1s orbitals alone, and then a sigma star 1s. So that star indicates that it's an anti-bonding orbital. A bonding orbital will have no star. An anti-bonding orbital will have a star.